There we go. Okay, so as we get going with this, I'll tell you a few details as people are still joining. Just in terms of logistics, the GitHub page, the ssc-datascience.github.io is where you can find all the code and slides and all the resources that we'll be using for this workshop. Okay, so this section here, the data science and analytics section, it's brand new. We just became a section in just the end of last year. And our goal really is connecting researchers, practitioners, people of all levels in data sciences, analytics, and really to exchange, develop ideas, to talk about some of the open challenges, to develop advances. We're really intending to loop together people in academia, government, industry, nonprofits, all sorts of places. And really in bringing people together, this is how we can exchange ideas, develop tools, talk about challenges, find out what each other needs. And so we're hoping that this section can be one new community to bring together the Canadians in this field. So along with that, this section definitely looks fun. How can you join? There's lots of ways to get involved. And first of all, you already are. You're here. You're at our workshop, which is fantastic. So thank you for taking that step and joining us here today. If you are becoming a member of the Statistical Society of Canada, or if you're renewing your membership, you can join our section. We do charge the fee of $5, so it's not huge, and any of the funds that the section has can be used towards. We can use them for things like developing new talent, educational outreach, opportunities for individuals. Our section is still developing, so we are still full of ideas and looking forward to taking action and trying to bring together the data science and analytics community, especially within Canada. On that note, you can participate in the section. We will have positions that are open in this. Right now, I'm the president of the section. Nathan Tabak, the co-organizer, is the incoming president. And we do have a few other positions as well. Shirley Mills is the treasurer, and Alberto is the secretary. So there's lots of ways you can get involved. This workshop is free. If you do find yourself with an abundance of funds or opportunities like that, feel free to donate to the Statistical Society of Canada. It is a charity and a non-for-profit, and there are a few ways that you can do that. Even better, convince your employer to do so, and that would be a great thing to do too. Today's workshop is split into two halves. Nathan will do the first half, and then at 2:30, if you're in Eastern time, is when we'll switch and we'll get into, and I'll take over for the second half. We'll have a little bit of break in between, so you can take a break in the middle time there. Okay, in terms of logistics, we will have the chat open for questions. It'll be moderated by one of us. All the code is available. Certainly try running the code as we go through the workshop, and hopefully that will generate more discussion and more questions. We already, I do see in the chat, have one person asking if international people or international members can join the Statistical Society of Canada and this section in particular. And absolutely they can. The section membership you do have to be a member of the SSC to be a member of this section. It's kind of a subsection of the Statistical Society of Canada. So, but there are no restrictions on where somebody is in order to join. Okay, the webpage ssc-datascience.github.io really is built from our GitHub page. So you'll have all the source code on the GitHub page, and this github.io page is the one that has it rendered so that it just looks pretty. But it is the same content that's there. Okay, so with that, I would like to turn the table over to Nathan. And Nathan Talbeck is a professor in statistics and computer science at University of Toronto. So what I'll do is I'll stop sharing and I'll give it over to you, Nathan.
Oh, thanks, Dave. So again, welcome everybody, and we're really happy that you could take the time to join us this afternoon for this workshop. I hope it'll be more of a workshop than a lecture. So as Dave said, we'll try to use the chat function where you can ask questions, and I'll try not to go too fast. So because as Dave said, if we were live in a classroom, we would probably be doing things much more interactively and walking around, and people would be running code, etc. But we decided that there's probably only so much we can do online, or at least give it a shot anyway. So let me start off by sharing my screen here. All right. All right, so you can see that, right? Okay, good. Okay, so yeah, so let me start off with an outline of what I'm going to be talking about this afternoon. So the title of the workshop is the analysis of unstructured text. So we're going to be doing it in R, and so I thought we'd start off by looking at some libraries in R for working with text and importing unstructured text into R. So there's several different ways you can do that. A simple copy paste using an external application programming interface, scraping a web page, or there's actually a lot of libraries built into R that contain data. And then one of the fundamental aspects of dealing with text is something called regular expressions. And then another fundamental aspect is text normalization, so which is also referred to as tokenization. Then we'll talk about n-grams, and then word vectors, how to represent documents as vectors and matrices. And that will lead us also to looking at a measure of the number of terms in a document, and then something called term frequency, inverse document frequency. Okay, so so what's an example of unstructured text? So at the time that I was putting this together, I was that letter from Donald Trump had just come out to the WHO, and so so if you look at the letter, oh sorry, and I should maybe stop here for a sec. So what you're seeing here is the RStudio integrated development environment, and on the right side are the rendering of the slides, and then on the left slide is the actual markdown of the slides. So, so you should be able to see both, and then I might run a few things as we go through the slides. So again, looking at this letter from Donald Trump to the director of the WHO, there's all sorts of things going on here. There's dates, there's numbers, there's text, so it doesn't really have a predefined data structure. Another example is this paper, essentially a meta-analysis, the evolution of reporting p-values in the biomedical literature, where they went through a large number of articles in the biomedical literature, and they looked at how p-values are reported. And they defined a p-value as you can see here, either with p, lowercase p, uppercase p, p hyphen value, apostrophe s, etc. And they essentially downloaded all these papers and then scraped out the content where they talked about p-values. And that scraping was done using something called a regular expression. I'm just going to have a look at the chat here. Sorry, I just seem to have lost my my chat window, but I guess we're okay. Ah, there we go. Sorry. Is it possible for you to zoom into your screen? Looks a little small on my end. I'm not able to hear the speaker. Okay, let me try this. Thanks. Let me just adjust here. How's that sound? Better? Okay, good. Sorry about that. Great. Okay, thanks. And then in terms of my screen here, how's that, the screen? Okay. Are you able to see the slides? Screen looks good. Okay. Code is too small to see. Yes, the code is small. I might just zoom in and out, but can you see the slides? Let me just try sharing the RStudio screen. Sorry, I'm just gonna, might as well work out these technical adjustments here. How's that? Is that better? Great. Okay, good. Okay, great. So there was one question about, are we expected to replicate the R code? Again, if we were live, I would slowly go through this and I would make sure Dave and I would walk around and we'd make sure that everybody could replicate the code. But unfortunately, given the time constraints, I'm just gonna run through a lot of this code, but I'll pause so that, that you can try to run a few things on your own. Okay, so, so back to this. So the last thing I was talking about was where unstructured text comes up. And then in terms of working with programming languages with unstructured text, two popular languages for computing and data are R and Python. We chose R for this workshop, but we could have easily done everything that there is in this workshop with Python. So some really useful R libraries for working with unstructured text are these following libraries that I happen to use. So base R is the standard R package that's been around for many years. Tidyverse, another one called Janitor, helps you make tables and has all sorts of other functions. Tidytext, which is a nice library for working with text. The Tidyverse, which isn't on here, but was in the set of libraries. Arvist is very nice for scraping, for dealing with HTML and scraping web pages. And then there's another one, Selenium, which is useful for programmatically navigating and scraping web pages. So importing text into R. So a simple way to do it is, is to really copy and paste. So if I have this tweet here from Justin Trudeau, and you see the text of the tweet over here. I'm starting the week with an update on the Canada Emergency Commercial Rent Assistance, etc. We can simply put it into R and save it as a string variable. We can save the link as a string variable as well. The number of replies as a number. The number of retweets, 116. Should have been 115. The number of likes, etc. And then the URL to the tweet. So one question that's typical in dealing with text is, how many words are there in, let's say, the tweet text? So what would you have to do? Maybe you could type into the chat. How would you figure out how many words are in the tweet text? TF? Tokenize at space, term frequency? Yeah, so somehow we'd have to take this text and break it up using something, and that something would probably be white space here, since the words are separated by white space. We can use the tidyverse package to do that. In tidyverse, when you load this library, it loads a number of other packages, for ggplot, this tibble library, tidyr, readr, etc., and all these other libraries. So tokenization in R, we can take the tweet text, put it into a tibble, which is basically the tidy version of a data frame, and then use this function from the tidy text library on nest tokens, and save the result in a variable called out, and we'll tokenize it with this predefined token called words, which essentially strips it, basically tokenizes it using white space. So then it breaks it up into these different rows. So I'm the first row starting, the is the third row, week is the fourth row, etc. So one row for each word. And then there's, you can see there's 22 more rows. And then we can count the number of words using this summarize function, together with this, this other verb, and open close bracket, which basically counts the number of rows here. So as I said before, tibble is the tidyverse version of a data frame, and in most use cases, the two can be interchangeably used. So pipe, this symbol percent greater than percent, is similar to function composition, where you have f of g of h as analogous to taking x, piping it into h, then taking the result h of x, pumping it into g, then you would have g of h of x, and then taking that result and putting it into f of x. So in this tidyverse language in R, this statement here, where we'd have summarize, and then we would input this function on nest tokens here, and then input the data frame into the first argument here, is the same as this statement using the pipe. So in the statement before, this was x, this was f, and this was g over here. So it's essentially a version of function composition, functional composition. Now we could have done the same using base R, using str split, unlist, and then length, and we get the same result as that would count the number of words. So there's really nothing unique about a lot of the tidyverse functions, but it's just a different way of doing things in R. So, and then there happens to be a whole manifesto by one of the main authors of the tidyverse, Hadley Wickham, and these are his 4 basic principles. Reuse existing data structures, so you don't have to redefine data structures. Compose functions, simple functions with the pipe, so breaking things up into these simple functions, and then compose them. Embrace functional programming, so so the main unit of analysis, if you will, is a function instead of a variable. And then design for humans so that the code is very readable. And then the idea is that this code in the middle over here should be more readable than the top code or this code. So that's one of the main principles. Now, of course, it's very hard to read if you don't know what the pipe is. But once you figure that out, it comes pretty quickly. What libraries, what libraries need to be loaded for the code to work is a question in the chat. There's the email that Dave sent out earlier has all the libraries that you would need to run this code and that you would need to run the code that Dave will show you in the next part. So using an external API to access data or unstructured text. So R has several libraries where really the objective is just to import data into R from an external website such as Twitter or PubMed. So this RTweet library allows you to actually access the Twitter application as a programming interface and allows you to ingest tweets into R pretty easily. So the setup for that is to create this token. And I'm not going to go through that here now, but if you look at this article here that I put a link to, you have to go through some steps in Twitter and essentially create these two variables called the consumer key and a consumer secret. And then I've done it, and then I usually save those things in a separate R file called that I've called here Twitter_creds. So what I've done here is on the day that I did this, I scraped 20 tweets searching for Justin Trudeau, and I saved them in a file, and then I read them back in, and that file is in the GitHub repository. So here we can actually look at the file over here. So it has the user ID, the status ID, created at, the screen name of the person, and then the actual text, the source. What else is interesting here? Is it a retweet? The number of times it was favorited, number of times it was retweeted, etc. And so again, we can take the text from that and unnest it and count the number of words in each tweet. So among the 20 tweets, and then here I'm displaying the first 6 of them. So N here is the number of words in each tweet. And then since we have the number of words, we can plot them. So it looks like, it's mainly, somewhere around like 40, 45 words per tweet is typical. And so here, just let me explain some of this tidyverse stuff. So here in the first line over here, I'm saving a separate column as a row ID. And then I'm tokenizing it. And then basically I'm counting the number of rows to count the number of tweets. And then I'm taking that, this is saved as a data frame, and then I'm inputting that into ggplot and displaying a histogram of the number of words. So N here is the number of words per tweet. And then on the y-axis here is the number of tweets that I'm analyzing, which is 20 in this case. And then we can look at the relationships between number of words and other variables by looking at a scatter plot of the retweet count and the number of words. Again, using ggplot, but this time but this time I have to rejoin it with the text counts, and then selecting those two variables, the number of tweets and then the retweet count. I end up using this this geom point, which basically displays a scatter plot. Okay, so Twitter also suggests that best practice is to use hashtags that are all caps. So these are the hashtags that that were used in those 20 tweets. We can check, you know, how many of them were uppercase. So in this function here, this function here, toUpper, basically it returns a Boolean value, so that if it's true if it's an uppercase, and then it's false if it's a lowercase, if it's not all uppercase. And so I'm checking if that's equivalent to the actual hashtag, and I'm going to remove the number of missing ones. So 2 of them were actually uppercase. There were 20 in total, so about 10% were uppercase, if you look at the total number of tweets. Sorry, I'm just going to read the chat. Sorry, I think I missed this. Where can I find the file? So there was a question, where can I find the file twittercreds.r? So Twitter creds are my Twitter credentials. In order to set up those Twitter credentials, you'll need to go through the steps of creating an account on a Twitter developer account. Okay. So there's various R libraries for working with unstructured text. A few of the examples include Genius R for song lyrics and Gutenberg R for literature. Project Gutenberg is a free library with mostly older literary works, although there's several non-literary works. There's about 60,000 of them. And this package Gutenberg R is a package to help you download and process these works. So here I'm loading the library here and looking for any works by Einstein. And I come up with 2, relativity, the special and general something. And then the second one I came up with was Sidelights on Relativity, which is a talk by Einstein. So you can use the package to actually download the text of the talk. And then we can easily, using this tidyverse lingo, take the data frame. So Einstein talk over here. So this is what it looks like when I downloaded it from Gutenberg. You can see over here, so it has the Gutenberg ID, and then basically it has one line. It's broken up into lines. And this is the text of his talk over here. I'm unnesting the token, so I'm tokenizing it. And then counting the number of tokens, looking at the top 20 over here, and then plotting it in ascending order as a column plot. And then what you see here is you see that what are the top 20 most frequent words here? The, of, to, in, is, a, that, etc. So a lot of the words that you would consider, they're common, but they're not that informative about what the text is about. So, so this is a common problem in looking at unstructured text. So we can remove the stop words such as the and it by using, by somehow merging it with a data frame of these common, what are called stop words. So in the tidytext library, there's a data frame of stop words built in and called stop underscore words. And so A is able, about, above, etc. recording. And so we can remove the stop words by doing an anti-join, counting the number of remaining words, then looking at the top 20, and then plotting it over here. And then, so then what we end up with is ether, geometry, theory, space, bodies, relativity, matter, etc. So things that you would think that Einstein would be talking about. But of course, in a lot of contexts, maybe it's not appropriate to remove stop words. Sometimes they might be important since they're so frequent. Another way to get text is by actually going to a web page and somehow scraping the information from there or extracting it, what's called web scraping. So the Stanford Encyclopedia of Philosophy is the website that I decided to look at, and it's this dynamic reference that maintains that's basically peer reviewed and has a lot of entries on philosophical topics. So you can ask the question, so which philosophers appear most frequently in the Stanford Encyclopedia entries? First of all, you would need a list of philosophers, and you can do that by scraping a few Wikipedia pages using this R library called Arvist. So here, I'm just gonna share my screen, this other, let's see, new share. Over here, here. Oops, here we go. So this is the Wikipedia page. And so what I'd like to do is this has a list of of many philosophers. And what I'd like to do is I'd like to take all these names. So Adi Shankara, Nicola Papagano, etc. And I'd like to put them in a data frame. So somehow get the names from here into an R data frame. And so that's what's often referred to as scraping this web page. And this page goes on. And these are the names from A to C. And then there's a similar page for D to H. And there's another one, I to Q, and then R to Z. So, so the first thing that you can do is, and I'm not going to get much into HTML here, which is the language that web pages are written in, but we can do a few basic things with a browser. So what I would encourage everybody to do is go to this URL, and I'll put it in the chat here. I'll just give you a minute to do that. Okay, and then if you haven't done this before, what you can do is, so I'm using Google Chrome, but I think the same thing should work in Safari or in Firefox. I'm not sure about Microsoft Edge, but I'm sure there's something like it. You can inspect this element over here. So if you hit that, then you'll actually see the raw code for the web page over here. And so you can see what I'm highlighting here as I move my mouse pointer on this page in the inspect element, different things pop up. So for example, LI over here, I want to point, but it refers to a list element. And up here, UL refers to an unordered list. A is typical, it's the A tag, it's for referencing web pages. So what I want to do is I want to basically take off from this web page all these LI elements. Over here. And one handy feature of this is right here, you can see it where my mouse is here, just down here, where you can see this whole kind of path of how the web page is structured. And so now let me go back to my R screen over here. Okay, so that's what, where am I? Right, so that's what this, this screenshot shows you, is basically me inspecting the element and then looking at the, what HTML, what they call like a tag, corresponds to this line here. So the names are stored in this HTML unordered list. So that's UL, is the unordered list, as items, LI. Those are the list items, LI. So you can extract these nodes using a function called HTML nodes, then extract the text from the nodes using HTML text. So down here, in this, over here, I'll just highlight it. So I'm just loading the library Arvist. The URL to the web page is saved as a string. Then the next line over here is I'm reading in the web page into R, and I'm calling that wiki_fillnames AC. So if you look at this, if I inspect that element here, oops, it's going to have a head and a body with all these divs and these various attributes. So it's not very user friendly the way it looks. But what I can do is I can take that web page using this Arvist library, and then I can find out which part of the web page I want to extract over here. And that comes from this part of the web page over here when I go back to inspect. So let me do that. Let me share. Share over here. So over here, I see this, you see what I'm highlighting here. If you can see that little box that's popping up, oops. Back to that. You can see here, it has this div.mw -parser -output. That's the part that I want to extract. So I'm just going to go back to my sharing. Okay. So, so that's why I have this part here. That's the node that I want to extract. And then each of the nodes is going to come with some other stuff, but I really just want to extract the text. So that's why it's HTML text. And then I'm going to show you head is basically the first 6 lines of what I've extracted. So what I've extracted here is I ended up extracting article, category, glossary, outline, portal, etc. And then I get down to Adi Shankara with the entire line. I can remove the first few rows by using the slice function. So I can wrap this whole thing up into a function for doing this for all the 4 web pages. So again, this function takes a URL, so the URL of the web page, and then the rows that I want to remove, and then reads it into, so then I read in the web page, extract the part of the web page that I want to extract over here, which is what we went through before. Extract the text over here. And then what I'm doing here in this Tibble statement is I'm saying, take the text that I extract and create a column named names and put it into a data frame. And then over here, remove those first 5 rows where it had article, categories, etc. And then just return the actual names in the function. And so then I can do that for all the 4 web pages over here. So from A to C, D to H, I to Q, R to Z. So those are all those 4 web pages. And so if you run these functions, you'll extract the names from those 4 web pages. But now I basically have these 4 separate data frames and I want to merge them all together. I want to bind all the rows. So I can use this function called rbind over here that I've highlighted in yellow. And then I can look at the first 6 rows of this data frame here. So I have what I said I was going to have is the first row, the second row, et cetera, except I have a little bit more than the names. I have the name, and then I have some other text about the time that they were alive. So everything after the comma. So, and I really just want the names. So how can I get the names? I'll let you type in to the chat now. Yes, thank you. Yes, remove everything after the comma. That's exactly what I want to do. And any thoughts on, yes, only retain things before the comma. Great. And so, so how can I remove everything after the comma? Use a regular expression. Yes. Yes, and that's exactly the plan. So over here, and that's where regular expressions really come in really cleaning up a lot of unstructured text data. So here, this regular expression, which I'm going to talk a little bit more about later, this comma dot star $, is an expression for removing every character except a new line till the end of the string after the comma. And I can do that with this function called string removed. And so here, if I do it to all the names in that data frame, then I remove them all. And then notice that str_remove is also vectorized as well. And so it returns, it just returns the names. Okay, so now I've got a data frame full of names. But what I really want to do is I want to take those names in order to look at, my original question was, well, how can I look at the number of entries where those names are? And so, so what I can do is I want to somehow get those into the Stanford Encyclopedia of Philosophy. So I'm going to switch my sharing here. Hold on. Good, okay. So here. So what I want to do is I want to go to this website and I want to programmatically search all those, I think there's like 171 names or something like that. And I want to figure out how many entries these, when I search, I want to figure out how many documents the names are found in. So that's what I'm going to do with this package called rselenium. Okay. All right. Okay. Okay, and so workshop in and of itself, or at least part of one, but we can use the tools to basically automate this kind of navigating this website. And it's not primarily used for that, but it works very nicely doing this. So to run the R Selenium server, basically what I'm going to do is I'm going to run something called a Docker container, where I'm basically going to run a version of Firefox to actually go and load up the web page, navigate, and then type in all those names. So if you, this is on my Mac operating system here. So if you run this command, you'll run a version of Firefox, and then you can use this library. So this is like a bash command or in the Z shell or something like that. Yes, in terminal. So actually, since we're on that, let me just share something else. Desktop, terminal. Oops, no terminal, share. All right, right, so here, so I did it before I started this workshop, but I have a Docker container running here. So here, it's already running over here, and it's available on this port. And so that's what I'm going to be, that's what I'm going to use to navigate the web page using R. So let me switch back to R here. Share. All right. So let me just let me run through this briefly. So this sets up a driver, opens a connection to the server over here, navigates to this site, the plato.stanford.edu. Then what this does is it finds that actual search text, like that, the dialog box where you type in the search text. Then what I'm going to do is I'm going to input the first element of the names over here from the wiki names. That was that Adi Shankura. Then what I'm going to do over here is I'm actually going to find the button element over here, and then I'm going to click the button. So this is all done programmatically. I'm actually not physically doing this, but programmatically I'm doing it. And this is actually a screenshot from the R Selenium package. So this is what you found, and this is what I showed you in the browser window. So you can see here 1-10 of 17 documents found. So now I want to figure out, hey, which part of that web page is that 17 on? So again, I can go inspect the element, do what I just did before, and I find that it's in this div, and the name of the div is called search total. I don't know if you can see that. Hopefully you can kind of see that over here. It's called search total. So then I can use this find elements method in the R Selenium package to actually go get those lines and then extract the text. And then the text that I find is that 1-10 of 17 documents found that line in the HTML page. So that was back over here. That's what I'm extracting, just this line. Okay. And so, so now what I want to do is I'm going to have to somehow extract the number 17 from that line. What I can do is, again, I can write another regular expression, which I'm going to go through quickly later. And it turns out to look like this. So basically, find all the digits before the word documents. That's what that says. Okay, and then I can write a function to automate this whole thing. So basically, to take all the names in the data frame, programmatically plug each name into the Stanford Encyclopedia of Philosophy, then extract the number of documents that it finds. And that's what this does. It basically just puts all this into a function. And then notice, I guess one thing about this is I put a kind of pause in the function so that I'm not hitting the website continuously. It kind of mimics a bit of a human. And then what I've done here is I've only did it for about 10 names because it takes a while to run. Then what you could do is you could plot a frequency plot of the most frequent names found over here. Okay, regular expressions. So I'm going to go through these really fast, but obviously there's a whole another workshop that we could do here. But what is it? I'm sure some of you have seen it before from what I can see from the chat. But it's a formal language for specifying text strings. So basically, how can you search for versions of cat, cats, cat with an uppercase C, and then cats, uppercase C, and then an apostrophe, and then an S as well. And yes, that's my cat. So one thing in R, if you've used regular expressions in other languages, is the 2 forward slashes represents 1 forward slash. So that's something to keep in mind. And so for example, /W matches any word, and then /uppercase W matches any non-word character. So, so this string view function is a kind of handy dandy function in the stringer library. So here, looking at this string, do you agree that stats is popular? I'm looking for every word basically. So you can see it highlights every word. What doesn't it highlight? It doesn't highlight the spaces in between the words. And it doesn't highlight the question mark at the end. And then there's other kinds of ways to find different characters. So lowercase d, uppercase d, dot, S matches any white space, etc. There's ways to specify looking for like lowercase c and uppercase c using brackets or this thing called a pipe. Ranges of things, because sometimes you don't want to input all the numbers from 0 to 9, so you can specify that as 0-9. And then R has these POSIX characters, this full colon, alpha, full colon. And probably the best way to get familiar with all this is to look at the cheat sheet. I know that sometimes when I haven't used them in a while and then I have to go back to them, I find this cheat sheet really handy. So I'm just going to show that to you on here. And I put it up on the website as well. So here, this cheat sheet really has a lot of stuff here. Over here. So you can see a lot of what I'm talking about, the different characters that you can match. So for example, /S is any white space, /D is any digit, etc. So that's really a great reference for that stuff. All right, let me go back to R. Okay. So here, this caret here, when it's inside a bracket, basically means negation. So caret XYZ means neither X nor Y nor Z here. And on the other hand, if caret A is at the start of a character, then it matches something at the start of a string. And then $ matches at the end of a string. So if you wanted to look, look in these 2 strings here, like xenophobia causes problems, capital X xenophobia causes problems, you could look at this pattern here. So matching X at the beginning of a string or S at the end of a string. And then of course the X here is a lowercase x. That's why it didn't match in the second one here. If you wanted to quantify, so question mark, star plus, or then just curly braces and then a number matches the number of a certain type of character. So for example, here, this pattern over here, where I have color and then I have U and then a plus, stands for the regular expression 1 or more U's. So that's why it matches this string and this string, but not the middle string. And it's nice to also have a way to group things. So precedence, so how can I match puppy and puppies? You can put a round brackets around the Y and IES, and then add an OR over here. So that example from the p-value paper that I was talking about before, they used a big regular expression to basically scrape a lot of biomedical papers here. And that expression, you can see it over here, is right in here. It's actually in the appendix of the paper, of the paper from the Journal of the American Medical Association. And so just to kind of, these things can get quite complicated. So here, what the first part is referring to is white space, which is the /s, or with the pipe, a left round bracket. And then square bracket, uppercase P, lowercase p, and then curly brace 1 matches either uppercase P or lowercase p. The next one is either white space or hyphen 0 or more times with the asterisk at the end. Value or values, 0 or 1 times. And then /s is white space. So, so here I go through an example of, I actually took the regular expression from the paper and I plugged it in here, but I didn't end up picking up this. So I'm posing this question here: what needs to be added to the regular expression? And the thing that needs to be added is this thing in the OR. And then you would pick them up. So I don't know if there's a mistake in that paper or what's going on, but it'd be interesting to look at it a little bit further. N-grams. So n-grams are basically a sequence of n words. So 1 gram or unigram is a 1-word sequence. 2 gram or bigram is a 2-word sequence. 3 gram or trigram is a 3-word sequence. So suppose you want to compute the probability of a word, let's say W, given some history H. So the sentence, "He had successfully avoided meeting his landlady," is at the beginning of Crime and Punishment by Dostoevsky. And if you've read this book, then you know that there's a lot of talking about a landlady in this book and what happens to her. So, so let H be the sentence, "He had successfully avoided meeting his," and W is landlady. And then if to compute this probability, you'd want to somehow estimate, let's say, the relative frequency of counts of "he had successfully avoided meeting his landlady" divided by the number of "he had successfully avoided meeting his." You could do this just say by, hey, searching Google. But new sentences are created all the time, so it'd be kind of difficult to estimate doing that. If you want to know the joint probability of an entire sequence of words, like "he had successfully avoided meeting his," out of all possible sequences of 6 words, how many of them are there? So you want to compute the probability of landlady given "he had successfully avoided meeting his." So we could structure it like this: landlady given "he had successfully avoided meeting his." What the bigram model does is it approximates this probability using the Markov assumption. So assuming that everything except the last word is really important. So how can you compute this? So count the number of bigrams that are "his landlady." Count the number of bigrams that have first word as "his" and then something else, and then take the ratio. This can be done in R. using the string detect function. So over here, I'm looking at all the bigrams, his landlady. And then this one over here is detecting the number of bigrams just starting with his. And then looking at the number of bigrams that actually just start with his. And then what I end up doing is looking at the ratio. So it's a very small percentage. So it's only 10 out of the 200 or 2100. So it's only 0.005. Word vectors and matrices. So the big idea here is that words occur in similar contexts, have similar meanings. So the idea is that a word is characterized by the company it keeps. So for example, oculist and eye doctor tended to occur near words like eye or examined. So this link between similarity in how words are distributed and similarity in what they actually mean is referred to as the distributional hypothesis in linguistics. So a computational model that deals with these different aspects of word meaning is to define a word as a vector in n-dimensional space, but the components of this vector can be thought of in various different ways. And Dave's going to get more into this in the second part. So to start off with, we can look at, as a very simple example, how often do the words term the words, or in other words, what they call terms, these words battle, fool, good, and wit, how often do they occur in these Shakespeare plays? As You Like It, Henry V, Julius Caesar, and Twelfth Night. So I'm not going to go through all the code here, but essentially what this is doing over here is this is downloading the books from Gutenberg, then adding a column that labels the book. And then you'll see the slice here. And what that's doing is it's slicing off a bunch of the text that says, you know, you've downloaded this from Gutenberg, et cetera, et cetera. And then I'm going to bind them and put them in a big data frame. And I'm going to call that big data frame these 4 Shakespeare books. And then what I've done here is I've basically counted the number of times that these words occur in these plays. And so what you see here is that good occurs, is the most frequent one in all the plays. This matrix over here is an example of a term document matrix where each row represents a word in the vocabulary, and then each column represents document from some collection of documents. So this table above is obviously a very small selection of the larger document term matrix if I were to look at all the terms in these books. And I think it would be quite sparse, this matrix. And then a document, what this does is it represents a document as a count vector. So if absolute value V is the size of the vocabulary, then each document has that number is a point in that dimensional space. And then the last thing that I'm going to go through is something called term frequency inverse document frequency. So simple frequency isn't the best measure of association between words. So one problem is that raw frequency, it's kind of skewed and not very discriminative. The dimension for the word good is not very discriminative between the Shakespeare plays. It's basically just occurs frequently. So it's a little bit of a paradox, so that words that occur nearby frequently are more important than only words that appear once or twice. But on the other hand, words that occur too frequently are unimportant. So we kind of want to have a way of balancing these two conflicting constraints. So we can look at term frequency, and term frequency can be defined in various different ways. And the reason I'm defining it as as this is because this is the way it's defined in the tidytext library. So basically, it's the number of terms in a document divided by the sum of the terms. So here, to make this concrete, so if you looked at D as you like it, if that's the document, and T is battle, that's the term that we're looking at, then the term frequency is just 1 over the sum of those frequencies. Inverse document frequency, terms that are limited to just a few documents are useful for discriminating, because if they only occur in a few documents, then it's a way to tell those documents apart from other documents. This idea of inverse document frequency is basically the number of documents divided by the number of documents containing the term, and then looking at it on the logarithmic scale. And then finally, TF, IDF, or term frequency, inverse document frequency, is the product of these two. And in R, using the tidytext library, this function that I've highlighted over here, bind underscore TF IDF, is a way to, in a fairly simple way, compute the TF IDF for terms in several documents. And so what we can quickly see from this table is that, going back to good, is that good over here has a very high term frequency. So that's this column over here, TF, but very low TF IDF. Whereas battle has a much higher TF IDF. So, so maybe battle is a better discriminator of these 4 documents. And again, we can look at this graphically here. So you see the same picture. So on the left panel here, I've plotted term frequency. And then on the right panel, I've plotted the corresponding TF IDF. And you can see the discrepancy between just looking at frequency and looking at TF IDF. And that's it for part 1. So I'm happy to take any questions that you want to type into the chat. Okay. You're welcome. And one question is, can I discuss R-Selenium again briefly and the importance of Docker to R-Selenium? So let me go back to the R-Selenium bit. So I'll put this link up, but this is the part with R-Selenium. So over here. So basically, a Selenium server is it's a standalone program that allows you to run an HTML test suites in a variety of browsers and OS combinations. So the way to run this Selenium server is you can either download the Java program and run it on your computer, or you can do it through something called Docker, which basically just contains an entire computing environment with Firefox set up. Then R connects to that in that Docker environment and can run things. So you don't have to worry about installing the actual Java program. So that's the short answer of that. Just looking at this one. What are the
just in terms of just as I've been moderating the chat, there's a couple of interesting ones. There's one here about ethics and robots.txt.
Yes. Yes.
Do you mind
yes.
a few words about robots.txt kinds of things?
Sure. It's a great idea. So I'm glad somebody brought that up. And typically, I don't like to extract information from a website using a program that has a robots.txt where it doesn't allow that. So I'm pretty sure, I hope I did live here. I'm sharing my this with you, but you can look at robots.txt over here. And what this tells you roughly, without getting into all the stuff about robots.txt, is it says you shouldn't write a program to scrape archive, CGI-bin, diffs, inc, refer, temp, usage, all these other things. But it doesn't say anything about the other parts of the Stanford Philosophy Encyclopedia. So I think it's okay. I mean, it's from what I understand. And I also had a look at the other thing that I typically have a look at as well is the terms of service, which is sometimes on a page and sometimes isn't. I didn't see anything here, but I usually have a look, especially before I do something in public with scraping websites. But those are the two things that I usually have a look at is robots.txt and then any kind of terms of service thing where they ask you not to scrape information. So in terms of R Selenium, I think the same principles would apply to any kind of scraping, and it's not specific to R Selenium. Oh, I see. The robot.txt says disallow search. Yes. Yes. So actually, to be honest with you, I missed that. And I forgot that I was using R Selenium to search. So to be honest with you, this would be against the what they've asked people to do. So I don't think it would be quite right to do this. So so maybe I should modify that part of my code. Thanks for pointing that out. I think I was, yeah, sorry, go ahead.
I was just going to say that the second part will be starting up at around 2:30. So feel free to ask a few more questions or take a few minutes break or whatever works.
So when using TF-IDF, there's no need to eliminate words that have very low frequency from the bag of words. That's right. There's no need to eliminate words that have low frequency. Can we have a bit more math intuition for TF-IDF? So maybe I'll just go back to, oh, sorry, I'm not sharing the right screen. Or reference to it is fine. Yeah, I can, I can probably the best thing to do in terms of time is to post a reference to it. How do you keep track of or find out about good R libraries? Oh, I don't know. I get, I guess people tell me about them, or sometimes on Twitter I find out about things following hashtag. Twitter hashtag #RStats. It's a good way to find out about yeah, I see somebody's having problems with getting rSelenum to work in Windows. Yeah, I think I remember reading that there were some tricky things about getting rSelenum to work in Windows. Any reason to switch? Oh, sorry. There's a question about getting switching over to Python. Switching over from Python to R. Is there any reason to switch over? No, there's no reason to switch over. There's nothing that you can do in R that you can't do in Python, unless you really like using the tidyverse or that suite of libraries. Is it necessary to use tidyverse commands, or can older R syntax be used? Older R syntax, I think, could be used for almost everything I've done here. If not, I can't think of anything that requires the tidyverse syntax. The brackets. There's a question about the Wikipedia page. So I just took this page here. Let me kill that. Over here, and I'm just gonna put it back into the chat. Sure, why it puts that extra bracket there, but maybe it shouldn't be there. So I wonder if now's a good time to take a break until, what's the difference between stemming and regular expression steps? You explain things. So regular expression, you can, I would think of regular expressions as probably, you could customize the types of stemming that you wanted to do. So I think regular expressions is a little bit more general. And my understanding of stemming is that you would remove the ends of words. So like ing, plural s, things like that. Where you could do that in a regular expression. You're welcome. Okay, so so Dave, maybe we'll break for 5 minutes and then come back at 2:30.
Sure, that sounds good. I can share that sort of welcome slide again for the next
Sure.
minutes, and then
That's
that's about
great.
a 5 minute break, and then we'll jump back in there.
Sure, sounds good.
Thanks, Nathan. That was fantastic.
Oh yeah, thank you.